At the microscopic level, every digital device relies on a strict traffic cop to regulate the flow of electricity. It's called a diode. This component has a long distributed lineage. It began in 1874, when German physicist Ferdinand Braun documented that electrical current flowed in only one direction when he poked a galena crystal with a metal wire. By the early 1900s, this physical quirk was being used in early radio technology. Operators relied on these crude, delicate cat's whisker detectors to snag signals out of the air. The turning point arrived in 1940. While testing a slab of silicon at Bell Labs, electrochemist Russell Ohl discovered a natural boundary inside the crystal that governed this behavior, the p-n junction. This p-n junction acts as a one-way valve. Push current forward, it flows easily. Push it backward, it hits an impenetrable wall. Force it with enough pressure, you hit the reverse breakdown voltage. The component literally shatters under the strain. This predictable obedience to classical physics made early computing and radio possible. But as technology advanced, that rigid physical barrier became a speed limit. After World War II, the engineering world raced to master microwave frequencies to build advanced radar and high-capacity communication networks. But standard diodes were simply too slow. Relying on electrons to physically climb over a resistive barrier takes a measurable amount of time, making them incapable of oscillating at microwave speeds. So researchers in the 1950s started asking a different question. What would happen to electricity if you engineered a p-n junction to its absolute physical limits? To build the high-speed communications of the future, they realized they had to deliberately circumvent the one-way rule they had just spent decades perfecting. In 1957, while working at Sony, physicist Leo Esaki began experimenting with aggressive diode designs. He took the standard manufacturing process and cranked it up, intentionally doping the silicon with exceptionally high concentrations of impurities. This heavy doping forced the central barrier of the p-n junction to compress, shrinking it down to an unimaginably thin 10 nanometers. By squeezing the barrier to that extreme atomic scale, Esaki shifted the behavior of the current from classical motion to quantum probability. Because the wall is now so incredibly thin, an electron doesn't need the energy to physically climb over it. Instead, it simply bypasses the space entirely, disappearing on one side and instantly rematerializing on the other. This is quantum tunneling. This tunneling effect unlocked a unique electronic property, a phenomenon called negative differential resistance. Inside this specific operational window, the component behaves counterintuitively. Pushing more voltage into the device actually causes less current to flow through it. And because of the energy states inside the heavily doped crystal, the diode also conducts perfectly in reverse. Its reverse breakdown voltage is exactly zero. By pushing silicon to its absolute extremes, Esaki had engineered a one-way valve that conducts backward and resists more as you push harder. His work earned him the 1973 Nobel Prize in Physics for the experimental demonstration of electron tunneling. Because quantum tunneling happens almost instantaneously compared to normal conduction, the tunnel diode achieved the speeds required for microwave oscillation. By the 1970s, it was a staple in high-performance hardware, like the front-end receivers of the Intelsat V communication satellite. It also possessed a physical resilience that standard silicon lacked. Relying on tunneling made the diode highly resistant to the ionizing radiation that would otherwise disable electronics in deep space. Manipulating junction physics in this way branched into a wider family of specialized components, harnessing the p-n junction to emit light in LEDs or absorb it in solar cells. Altering the microscopic architecture of a 10 nanometer gap ultimately dictated the specific capabilities that enabled high-frequency satellite links and modern optical sensors. But perhaps the most remarkable thing about the tunnel diode is its sheer physical endurance. Recent laboratory tests have shown that components manufactured over 50 years ago still function perfectly today. Because they rely on quantum mechanisms rather than degrading physical barriers, their shelf life is practically infinite. The tunnel diode proves that progress often requires looking past the established limits of classical mechanics and engineering a way to bypass them entirely.